thank you to all the organizers to give me the opportunity to talk about this topic that has been following us for, I would say, the last 15 years. I will be working with an example. So I want to really talk about the real practical application. And we are talking about a big application. So the software that we are using in weather and climate modeling at CSCS, and of course not only at CSCS, but in a larger collaboration that we have with the Meteorological Service of Switzerland, which is MeteoSwiss, and then the German partners that are in the boat of developing this. So this is this icon model that I will be talking about, which is an ecosystem for atmospheric and ocean modeling software that is used for climate simulations by, say, our colleagues at ETH Zurich and colleagues in Germany and kind of all over the world and all over Europe, definitely, as well as for numerical weather prediction. The development is several hundred people. The number of 200 may be actually bigger nowadays. The current ICON consortium consists of 4 German member institutions, and of course there are many other contributors, in particular ETH Zurich, CSCS, and MeteoSwiss. And we even are in discussions right now to become a 5th member of the consortium. We are talking about 2 or more millions of lines of code written in the past 2 to 2.5 decades. And it is, from a numerical weather prediction point of view, the successor of the Cosmo model that some of you have heard of in the context of GPU computing, and also an ECAM model that was used at Max Planck Institute for Meteorology in Hamburg. ICON in forecasting is used by the German Weather Service since about mid-2010s, and in fact, at MeteoSwiss, or with MeteoSwiss, we are about to introduce it now in operation. So it will go pre-operational actually it's going pre-operational on GPUs this month, and in early quarter 2 2024 it will go operational as a model. And there are prominent projects such as the Climate Adaptation Digital Twin for the Destination Earth project, or the XClaim project at ETH Zurich, that are also using the same model software. The makeup of a climate model, and I think they are all pretty much the same, they consist of a dynamics part that is typically is stratified, and then the physics part that models all the subgrid phenomena. So you have to imagine a 2-dimensional grid of columns. And the 2 models I've been mentioning, Cosmo, which is the one that we took to GPUs 10 years ago in our user program at CSCS, and then since 2016 have been running operationally on GPUs with MeteoSwiss. This model was ported to GPUs by rewriting, you can say, the dynamics with a domain-specific language using C++ and template metaprogramming, and OpenACC and OpenMP directives in the Fortran code that implements the physics model. Now, ICON is slightly more heavy on the OpenACC side, in that we chose both to implement both the dynamics and the physics with OpenACC directives. The history, and I think this is important for you to get the feeling, what is the effort involved behind this. So the Cosmo model, like I said, we worked on this in between 2010 and 19, where most of the porting actually happened in the first 2 or 3 years. And from then on, after about 3 years, it was operational in the user program. And it then took a few more years to do all the things for the operational numerical weather forecasting. But since 2016, like I said, we are on GPUs, and we are now, when I say we go to ICON, the Meteor Swiss model, go into the 3rd generation of GPU implementation in 2024. The ICON story is a bit longer and more complex. It started with, we were all in full swing of developing new implementations of the dynamical core. So we worked on the dynamical core of ICON with CUDA, Fortran, and OpenCL, but then the developers insisted that we stay on a directive-based approach. And that then led to a project, actually PRAISE, second implementation project funded by Work Package 8, which funded the development of the dynamical core of ICON using OpenACC directives. So this was in ICON, I think, the first big milestone that the dynamics was functioning with OpenACC directives on GPUs by the middle of the last decade. And then there was a German project called HDCP2 or Quadrat, and the GPU port there, though it was very competent and a big effort, it was unsuccessful. And the reason was that the development of the Fortran code was going too fast. So, and there was no real component testing infrastructure. This is an important lesson learned that I will come back to in later slides. And then we had the porting of the radiation module that's used, RRTMGP. This is an acronym I cannot remember, but when it's written here, I can see it. This is a radiation code that was developed at Max Planck together with Pincus and Norman et al. And then there was a project that we had funded in Switzerland that would take care of a lot of the climate physics parameterization beyond radiation and so on. So this all led up to by 2020, we were then ready, or our colleagues at Max Planck were then ready to run this implementation of ICON, first at CSCS and then later on the LUMI, not on the Joules booster at Jülich. And also in the last 3 to 4 years, Meteor Swiss, with the support of a lot of support from NVIDIA and some from us, brought the necessary numerical weather prediction physics also to GPUs. And as I said, it is going to go operational very soon. What we see here is just, the proof that this model is running on a number of architectures. Intel Haswell, the AMD EPIC, the NVIDIA P100, V100, A100. So you can really say we have achieved a portable solution to many architectures. And in recent years, there was a big investment also going to porting it to AMD GPUs. And this is the proof here. This is in the Destination Earth digital adaptation digital twin, the ICON model running on LUMI-G, which consists of, where a node consists of 4 AMD MI250X GPUs. So you can basically summarize this first part. You can say, okay, it took us 10 years, to get this onto GPUs, and a big effort at CSCS, Meteor Swiss, and then later also the people involved in this Destination Earth project. We did manage to really port it to many architecture. The risk, of course, of the whole thing is, particularly now on Lumi and AMD GPUs, is that we have dependency on a single Cray compiler maintained by HP, and those involved, they know that this was a difficult situation that we had in, and this is something that the Open Accelerated Computing Consortium should consider, the need to diversify or adopt OpenMP. I know this is a provocative question, but I hope to spur some thinking here. There are, however, two more issues or topics that we need to think about. One is what I will explain now, poor separation of concerns between directive-based software portability approach. It puts strong constraints on the original development. And the other one is that directives as such will not help with performance optimization. The first one, is just when you look at OpenMP and OpenACC implementation, you do have to change OpenACC compared to OpenMP. So you do the performance porting in these directives. And the question is, of course, when you do this, what happens if you start changing the original code? And this is what led us to fail in the first HDP2 funded project, that if the original code changes too fast, it's very hard to keep up with the performance optimization. And of course, the real code you have to look at are these things, where, because you have OpenMP directives, you have the OpenACC directives merged in this particular software, you even have NEC directives. And now the real question is, how do you maintain this? Because you have, when you keep evolving the model, and this is a real problem, that you have multiple software, multiple codes inside the same software files, and this becomes very difficult to maintain. Now, the second problem is this question of that my colleague Mauro Bianco calls, the von Neumann assumptions are no longer valid. We know that on our CPUs already, the original model of von Neumann does not introduce the concept of latency between memory and loading into the CPU. But in reality, of course, these things matter today. You cannot ignore them. And so the languages that were based on the original von Neumann abstraction when they were developed, they are not aware of where things are in memory yet. In order to write optimal code, you have to know. And so data in the languages, like in this case, C++ or Fortran, variables get declared before they are used. However, to place them properly in memory, you need to know how they are used. And then things get even more complex when you have parallel execution and distributed memory. Here, I want to just jump to the, you have to think about the dependencies, whether there are dependencies or not, and then the type of dependencies. And so the approach is typically, well, you can imagine having a compiler that does the analysis and then just creates optimal code. But this we know is hard and almost unrealistic. So we know that one thing that works is taking compilers together with annotated source code. So these directives that we have seen work. Now there are other approaches that I would like to suggest, and one that I've mentioned is this, the use of domain-specific languages, where you can put some of this domain knowledge about how data is used and and how it should be placed into the programming language, and that can simplify this analysis of the computation. Or you can extract patterns in data flow intermediate representation and have some performance engineer work on that. And so what I'm trying to propose now at the very end is that these two that are in green here, that they should be considered together. And my colleague Thorsten Höfler has put this slide together. And I wish I could show the builds, but then I cannot move back anymore. So the way you have to read this is here on the top left. You have this, the domain scientist is approaching the problem by implementing a model using a domain-specific language, or depending on the problem, MATLAB or TensorFlow or NumPy. And then there are research software engineers that translate these implementations using these domain languages into a parametric program graph, intermediate representation, that then is used by performance engineers who have, of course, graphical tools to analyze the performance and basically optimize the partitioning of the graph. Now, people who know will say, well, this is an NP hard problem, and this is true to find the optimum. But experience shows that an experienced performance engineer can visually partition a graph in a near optimal way, or with very satisfactory performance. And then behind that, you have code generators that then introduce the codes for the target architectures with the proper placement of data in a way that the normal compilers then can recreate this optimal execution. And what I'm doing, trying here, is to argue that setting up something that can implement this is actually not much more difficult than in terms of maintenance. Clearly, you need more than typically 1 or 2 people in your team. But I told you that, say, a large project like ICON has hundreds of developers. So it is not a problem to introduce a few tens of developers that work at this DSL framework level and performance engineering. And once you do that, the model developers actually end up working in a more descriptive language. And this will enable scientists to basically, or model developers, sorry, to even implement different models with the same DSL framework and performance engineering approach. And then if you use container-based deployment on the back end, you will be able to deploy your software on different computer centers and different architectures. So to summarize, I think I have to come to an end here. I'm running over. The OpenACC directives work for porting legacy software to GPUs, and ICON, running on A100 and MI250 is the living proof of this. DSL plus OpenACC, which we use in Cosmo, is difficult to manage in large collaborations, but is a viable approach too. Traditional languages have these problems of not separating concerns between performance engineering and application development or model development, and this inherent problem of not being performance optimizing. And that I believe, or we should consider this model of adopting a combined DSL and data-centric optimization approach, maybe in the future, and maybe this can be discussed in this open accelerated computing performance.